Hello, I'm Terry, and in this video we're going to write a reaction between a weak acid and a weak base, and to identify which one acts as the acid or the base and in which way the equilibrium will lie. So this is our example. We want to write the equation for the reaction between hydrofluoric acid, HF, so I'll write that there, and the bisulfite ion, HSO3-, so I'll write this here, HSO3-. Okay, and these are weak acids and bases. None of them are strong, so they're going to form an equilibrium. And then after we determine what this reaction is, we want to also determine whether the reaction favors the reactants or the products. So to know what we produce here, we need to know which one is the acid and which one's the base. Now it tells us that HF is an acid. So obviously this has to be our acid, so I'll put that here as acid, and I'll put the bisulfite as the base. But what if you didn't know? What if it was tricky? What if both of them could act as an acid or a base? Both of them were amphiprotic, if your teacher wanted to trick you. Well, we go to this acid-base table, if you're given one. Maybe you'll just be given the values, but sometimes you're given a value. And this is an acid-base strength chart, and it's based on Ka. So Ka tells you the strength of the acid, how strong of an acid it is. And the larger the Ka, the stronger the acid. So we have the stronger acids are near the top here. So these are stronger acids because they have larger Ka values. So we're dealing with HF and HSO3-. So let's look at where they are here. So HF, so this is acid, this is the conjugate base on this side here. So let's look at the acid. So HF is down here. Here's HF. And it has a Ka of 6.6 times 10 to the negative 4. Okay, now let's look for our HSO3-. So none of these are HSO3-, so we've got to keep going down. Here it is, bisulfite. So this is the other one. And 6.3 times 10 to the negative 8 is its Ka. So here, this is the stronger acid, and this is the weaker acid because it has the lower Ka acid. So maybe I'll just write that out. So the Ka of HF is greater than the Ka of HSO3-. It's all about Kas when we want to know about acid and base strength. Also pKa's, but Ka is a good one. Okay, so now that we know HF acts as an acid, even though it told us here, but if you didn't know, now you know how to check. And an acid is, in terms of the Bronsted-Lowry definition, an acid is called a proton donor. So it loses H+. So if it loses H+, then it becomes F-, because the H is now gone. And it loses a positive charge, so it's now negatively charged. And a base, the Bronsted-Lowry definition of a base, is a proton acceptor. Proton acceptor. So it gains an H+. So rather than being HSO3, it's now H2SO3. And it gains a positive charge. So if it's neutral or negative right here, it's negative and it gains a positive charge. So it's a -1, it gains a +1, it's now neutral. So there's no charge here. It's like zero charge, but we'll just kind of leave it blank here. Okay, so this is the reaction. So we did this part, write the reaction. Now we want to determine whether the reaction favors the reactants or the products. And if we really want to deal with the Ka and the Kb, which is tells us the strength of the base here. So this acid has a Ka, let's write Ka values here. Ka is 6.6 times 10 to the negative 4. And the base was, I got to flip back, 6.3 times 10 to the negative. Now this is if it acts as an acid, which it's not. It's acting as a base. So we'll skip this for now. And let's look at this here. So the HF is the acid. It turns into the conjugate base. And the base, this bisulfite, turns into the conjugate acid. And H2SO3, this is sulfurous acid, H2SO3. Let's see what the Ka of H2SO3 is. So here it is. It's up here, hey? H2SO3. H2SO3. It has a stronger Ka value, a higher Ka value than HF, so it's a stronger acid. So this is the strongest acid out of them. So this is the, write that, this is the strongest acid out of the other acids, well, the HF, because this is now a base. So this is the strongest acid. And because this is the strongest acid, you can think of it as it's going to overpower this one. So an acid is a proton donor. So the stronger acid will be able to donate its proton better, to a greater degree, than a weaker acid. So in order for the reaction to go to the right, this acid has to donate a proton. For the reaction to go to the left, this acid has to donate a proton. But this one's stronger. So it's like think of it like a competition where this one can donate its proton to a greater extent. So every time HF donates its proton to make H2SO3, this H2SO3 says, nope, I can donate a proton a lot better. You give me your proton, I'm going to get rid of it a lot easier than you can get rid of yours. And it gives its proton right back to form HF. So this is the stronger acid. So the reaction is going to favor the reactants here.